Okay, so we are now going to discuss about the performance quality metrics associated with object detection. Very, very important session. Okay, and few things we discussed. So one is the predictions will or the inference will create roughly like 2000 bounding boxes. You can think about it. If I have a selective search giving me 2000 proposals, and now how to remove some of the redundant bounding boxes. So I was introducing you to the concepts like intersection over union, and then suppress those with very high intersection of over union because they are very similar boxes. And then I also briefly told there is a measure known as mean average precision, kind of confusing term because mean and average kind of makes the same sense, and why mean average precision. So we will define this in this session. So let's quickly go into each of these aspects in more detail. Okay, so key metrics. So it's a bit of detour but very important. First, intersection over union. Okay, so let's go through the intersection over union in detail. So it's also known as Jaccard similarity or Jaccard index. Many people use different terms, but it's all referring to the same. What is it? It is just to measure. Let's say you have two bounding boxes in the image. How similar are they? How closer are they? How overlapping are they? Okay, so if they are very much overlapping, that means they are giving the same information. You may discard one of them. This can be also used to measure how closer is your prediction with respect to your ground truth, right? You have bounding box prediction, you have ground truth bounding box. You can see how much they are overlapping. If they are overlapping pretty much, that your prediction is spot on, right? So that's the idea. So this is the definition. So it is basically, let's say you have two bounding boxes A and B. So you basically find the intersection between them, which is overlapping, and you divide it by the union of both the bounding boxes. So basically kind of related to the area of your bounding boxes. How much area is intersecting and how much area is overall if you add the two bounding boxes. So you divide that, you get the IoU score or Jaccard similarity score or Jaccard index, and higher the score means the two boxes are very, very closer or similar or overlapping. Okay, so let's take an example. So this is the blue is your prediction, the green is your ground truth, and here you can see this orange shade is your overlap. And if you measure the IOU score, it comes to around 54%. So that means 54% there is an overlap kind of thing, and that's your score. So 0.54 is not a very high score. That means your prediction is a bit off compared to the ground truth. So if I kind of use a chord to calculate, a pretty simple chord here, I think it's self-explainable. So what you're finding out is basically the height and width of each of the bounding boxes, and then basically you can use that to find the overlapping area. So this height and width is basically the height and width of this overlapping rectangle. So that you can actually find out using a simple formulation like this. You just find the coordinates of this position, this position, this position, and this position. Then you can just find the height and width and multiply that to find this. So that's basically this operation. Okay, and then area of A is basically the area, the height of the box A multiplied by the width of the box A. Similarly, area of B, the second bounding box, is its height multiplied by its width. So total area will be area A plus area B, but then that will have 2 times the overlap area, right? Because the overlap area will be added 2 times. So you subtract 1 time, so that it's exactly the this particular place plus this particular region plus this whatever is outside. Okay, so then you have the intersection, which is the overlap area here, and you have the combined area plus some epsilon for division by zero issue. So you just do this, which is this formulation here, you get the IOU score. It's pretty straightforward. So if you have a slightly more overlap, so here it was 0.54, but now the prediction is closer to the ground box, you have 0.71 better, and this is what we expect. 0.91 is great. If you have a network which can give you like IOU score of 0.91, that means you're very close to the ground truth. Okay, so that's the idea. And of course, as I said, IOU score can be used for two purposes. One, for checking how good is your prediction, how close it is your ground truth. You can also use it for, let's say you have 2-3 bounding boxes which are overlapping and redundant. You can use the IOU score to remove some of those redundant boxes, for example from your region proposal predictions, because many bounding boxes will be overlapping. Okay, so two use cases. One is to measure the performance in terms of similarity or goodness of your prediction, because higher the IOU score, your prediction is more closer to the ground truth. The second is to kind of use it to distinguish or remove some of the redundant bounding boxes. So let me write down here. So it's pretty clear. One use case is you can use it to see the goodness of your prediction, correct? Because you can use it to kind of see how good or how close is your prediction with respect to the ground truth. The second use case is to suppress redundant bounding boxes, right? Because after your region proposal prediction you roughly have 2000 boxes and you don't want to keep all the 2000 boxes, so you just use IOU score. Higher IOU scores, which means they are closer boxes or similar boxes, you can remove some of them. Okay, so that's the idea and that's what we are going to discuss pretty soon. So let's go there, which is suppress overlapping boxes. And this is not measuring the prediction quality or goodness of prediction, but to suppress so many boxes which may result from your 2000 region proposal predictions. Because remember, during inference your process is like you pass the image through selective search algorithm which will give you 2000 predictions, then each of those crops from the original image you pass it through your CNN, which is the trained model, which will give you class plus your bounding box. So you have 2000 such classes and bounding boxes. You don't want to keep all of them, so how to suppress them? So here is the idea. Okay, so object it, so this is pretty much I have given. So this idea is known as non maxima suppression or NMS. So you can, so basically you are leveraging the IOU score to measure the similarity between boxes and you suppress the boxes which are having very high IOU scores because they are very similar. And this idea is commonly known as, or the jargon for the technical jargon for this idea is non maxima suppression, NMS. Okay, so let's see how it works. So first step is you have all the predictions done, you have stored the results somewhere, you go to those results, you select the highest scoring box. Okay, so maybe let's confine to one class, you need to repeat this for each of the classes. So let's say I'm interested in the class dog, so dog is your class selected. So out of all the predictions for dog class, you sort them in the order of the confidence score or the classifier score. Okay, and then you kind of calculate the IOU score with that highest scoring box with all other boxes of the same class. So all the bounding boxes associated with the dog, you find the IOU score. Now you eliminate all the higher scoring, actually there's a typo here, this should be higher scoring boxes, or rather here what they meant or I meant is lower scoring confidence score. So basically the classification score, not the IOU. So all the lower scoring, so maybe the ones with lower than your selected ones with a IOU threshold greater than zero point 0.7. So that means they all belong to the same object. They are all predicting the same object, but their confidence is lower. So, but their IOU score is very high. So I'll tell with an example. So very easy. So let's take this. So you have a dog prediction with 0.9 here and a dog prediction with 0.8 here and a dog prediction with 0.75 here and a dog prediction with 0.7 here. So you sort all of them and then you find that this guy is the first one to choose. So you choose this bounding box, okay, and that box is chosen and you find the IOU score of this box with all other boxes which are predicting as dog. So you find the IOU score with this blue with this orange, which is 0.78, this blue with this yellow, which is 0.07, and this blue with this dog, which is purple, which is 0.05, because they are a different dog, right? So you can see here. Now what you do, now you see whichever is greater than a threshold. Let's say I choose a threshold of zero point 0.7. So these two are not, so you will keep these two boxes, but you kind of eliminate this orange box, which is having a very high score. So physically speaking, this box and this box, the blue and orange, are going and predicting the same dog. So you can basically discard this particular guy, the orange. That's what exactly we are going systematically here. So you sort everything according to the confidence score or classifier score, take the highest one, find the IOU with all other for the same class, which is listed here, eliminate the one with higher threshold or whatever threshold that you choose. In this case, I'm going to eliminate that. So that's done. That guy is gone. Now you remove this. Okay, you no more consider this because this is done. Now the remaining you again sort, so 0.75, zero point 0.7, so I'll go with 0.75, of course only two of them, so it's pretty simple. And then you find the IOU score with the orange, so that is 0.74, and that's above 0.7, so you can literally eliminate this guy as well. So you literally can eliminate this guy as well. So you only have this guy and this guy remaining. So that's the idea. Okay. So this is what we call as non-maxima suppression. You suppress everything except the max guy. Okay. So that's the idea. So I'll kind of go through this code. I think that makes pretty much easy for you. So what we are going to do is you take all the boxes into a function with their prediction or classifier score, and then you kind of sort for the classifier. So sort the boxes based on the classifier score. Okay. So you can put a threshold for the classifier as well if you want. Okay. And then what you do is for each of these sorted bounding boxes, so you go and pop the highest one. Okay. So pop of 0, which is of course you have sorted the bounding boxes. The first one is popped out. So we are removing it from the list. So that first one is definitely the one with the highest confidence score, right? So then what you do is you kind of see whether that particular chosen box is uh, of the same. So now you kind of compare all other boxes in the list with this chosen box, but you also have to make sure that the boxes that you're covering are of the same class, right? So that is what this step tells you. So you only consider the boxes with the class of the chosen box, and then you measure the intersection of our union for each of those boxes using the function intersection over union function we defined in the previous slide. So you find each of those, and then you see only keep those with a threshold which is lower than the threshold. So you basically eliminate if the threshold is if the value is higher than the threshold, right? So that's what happening here. So you keep, and then of course you keep appending the chosen box, right? The others are removed already. So this is a very simple. So let me put it into simple steps here. So for each class you sort. So first step is you sort in terms of class score, right? And then second step, measure the IOU score of the chosen BB with all other BBs, right? Of the same class. That's important. That's why I put the class here. And then if IOU is less than a threshold, IOU is less than a threshold, you keep them because that's not overlapping. All others you remove. So this you repeat for each of the classes. So that's what exactly you are going to do, and it's a very very simple, very useful algorithm. Okay, so I hope it's clear, but assume this picture. You see this picture. If you are doing a face detection, you are in trouble. Even an NMS algorithm, a simple NMS algorithm like this may not help. You may need a more sophisticated algorithm because there will be a lot of predictions and you have to be careful here. Okay, so that's the idea. Okay, so now, so we discussed about IOU and how to use IOU for performance prediction, goodness prediction, and how to use IOU for suppressing redundant boxes, which we call as non-maxima suppression. Now let's go back to the first thing, goodness of prediction, and that's what we are going to develop here. That framework we will develop here. It's a bit complicated to start when you see it first time, but over the time when you use it, it becomes pretty clear. This is known as mean average precision. Okay, so MAP means mean average precision. Very important to note this. Okay, so mean average, they convey the same name, right? It doesn't make sense to how that usage in English, right? In that sense, mean average, what it means. Precision, you might have heard this term during your classifier, so it's very similar, the same thing. So what is mean average precision? So let me just break this term. The mean here means for classes or object types. So you need to have a mean across all the classes present in that data set. So if let's say it's a two class thing, dog and cat, you need to have something. So this precision, whatever we are talking about, the precision for each of the classes you calculate, and then you do across the classes also a mean, and that's what this mean means. The average means for the same class, each class you calculate the precision and you average. So mean basically means across different classes, average means within the class all the precision. So you average the precision within the class first, so that is average precision. Then you have multiple classes, you repeat that average precision for all the classes, all the types of objects present, average. So that's the mean. So mean of classes for each uh, for each class you do the precision. So first you within a class, within an object type, you do the precisions, average that, then you do that for all the classes, average that. So that's why it's called mean average precision. I hope it's clear, and if not clear you'll understand when we do some exercises. Okay, so mean of average precisions across all classes. So this mean is across the classes, average precision is across the precisions within a class. Okay, and then average precision, how do you calculate? So we are breaking down one by one from top bottom approach. Mean average precision, so for that we need to have average precisions across each class, right? So that's how do you do that. So how to do that is you have to plot something known as precision recall curve. An area under that curve will give you average precision, because area under the curve typically gives you the precision, sorry, average value, right? So that's the idea. Okay, and how to define precision? So for to calculate precision recall curve, you need to know what is precision, you need to know what is recall. You might have seen this from the perspective of classification, but let's do it from the perspective of object detection. Okay, so precision means true positives divided by sum of true positives and false positives. So what is sum of true positives and false positives? So you see, positives are with respect to the prediction, right? True positive means my prediction is correct. False positive means my prediction is wrong. So true positive plus false positive is kind of a measure of the total number of predictions. Please remember that. This is all predictions. Okay, the sum of all predictions. So if we have if done predictions on a using an object detection model, and if you have 100 predictions, that is the number that you put in denominator here, total predictions. Okay, so then what this entire ratio means, true predictions divided by total predictions. So true positives divided by total predictions. So out of all the predictions, how many predictions are true? Wow, that's something interesting, right? Out of all the predictions, how many predictions are truly positive? How many predictions are correct? So that is the term, the literal term precision, the precision of your model. The precision of your model is how many predictions are correct out of all the predictions. So true predictions out of all the predictions. So higher precision means my model predict most of the time very highly accurate. Okay, great. Now let's move to recall. Recall means true positives divided by true positive plus false negative. So false negative, true positive you already know, false negative, which means that your network is predicting it kind of, I mean, it's like not at all detecting in the case of an object detection model. Okay, so false negative, right? So it's really not predicting anything. So if you literally think what is this, true positive plus false negative, this will be equivalent to the total ground truth available, total number of ground truths which are available. Okay, so you are doing the ground truth, you are labeling it, so you have so many ground truths, so that is a total number of ground truths which are available. Out of that, how many of that is predicted correctly? So this is TP is true predictions, right? So here precision was with respect, everything was respect to the total number of predictions. Recall is more like total ground truths. Out of the total ground truths, how many are accurate or how many are true? So that is very important. That's why it's called recall, because high recall value means actually there is a problem, right? You are kind of in a situation where your prediction is a bit affected, right? You kind of recalling everything. So it's similar to the recall of cars, right? You recall a lot of cars means there are a lot of faults in the car. So similar to that, you can maybe an analogy to kind of remember. So recall will gives you a measure of how many predictions are true with respect to total number of ground truth. Precision means how many are true with respect to the total number of predictions. So precision is model's capability. Recall is model's uh, predictability or goodness with respect to the ground truth in that sense. So ideally speaking, you kind of want to be in a sweet spot. So something like if you have a model which is high precision low recall, so that means very few detections but accurate, right? Because recall is low, so that means actually you have to have a very good prediction rate, right? So both high precision low recall is kind of conservative. Your model is very conservative. It's not doing um, kind of not lot of uh, because few predictions will help you in increasing the precision, and less predictions will help you in increasing the recall as well. I mean low recall as well, right? So reducing the recall as well. There's less number of true positives. On the other hand, if your model is low precision but high recall, low precision and high recall, then that means the model is very liberal. It's doing too many predictions. Almost all the detections or actual ground truth are having some predictions, but too many false positives. So that's the thing. So what is a sweet spot? So that is where the map or the average precision helps. So you should have a very high average. So if your average precision is high, that means you are doing pretty good, because that's the idea, because that's a sweet spot that you want to be in, somewhere in the middle. Okay, so let me explain to you now. I think should have been done earlier. So what is true positive in the respect of object detection? So the red color is basically the ground truth, and the white color here is the prediction. So here, for example, the IoU between the prediction and the ground truth is 0.96, pretty high value, so it's a true positive. And if you see here, the prediction is way off, 0.22 only, so it's a false positive. And here the ground truth is there but prediction is absent, so it's something like false negative in that sense. Okay, so prediction is absolutely not there. So but in some of the calculations we use this scenario as a false positive also, because the detection can be somewhere here, right? Because many of the time this doesn't happen. The detections, probably you can say it's not detected as false positive also, because it's a fine line in that sense. Okay, so just some confusion can come there. Okay, so now let's come to one example. So this will help you. So you can see this video for the explanation as well, in case my explanation is a bit vague. So what's happening here is I have three images just for explaining it easy for you. And the green ones are the ground truth here, and the red ones are the predictions here. Obviously, you can understand by the false positive here, for example. Okay, greens are the ground truth and reds are the predictions. So let me put it into a table so it will be easy for you. So image 1, you have something with 0.3. This is a prediction. This is 0.3. It's false positive. No question about it. Another one with 0.6. This is that bounding box. It's also false positive, because you can see it's way off. Okay, so this is confidence score, by the way, the classifier confidence score. IOU score I'm not showing here, but some kind of as a human we can say they are way off, right? So I'm just classifying it as false positive. Of course, in your code this should be based on your IOU score. Okay, I just explain this for just illustrating this. Okay, so they are way off, so I consider it as false positive. Then 0.71, it's kind of closer, so I'll consider it as true positive. Okay, so that's the idea. For image 2, only one prediction, and IOU score is 0.5. I mean the confidence score is 0.5. The box is pretty much okay, so let's consider it as true positive. Last one, there was 1 2 3 predictions. First one 0.2, definitely false positive. Second one 0.8, very high confidence, but it's false positive because it's way off. And then the other one 0.9, and it's overlapping, so I consider it as true positive. So this is the full list, and this is a starting point for us. So your code should take the labels and the scores and then prepare a table like this if you are making a function for mAP. I have a code, I think I listed somewhere. Okay, so I'll show you that as well. So total number of ground truth detections in this case 1, 2, 3, 4. This is important because this forms the denominator for the recall calculation. And total predictions, we have 1, you can see it here, 3 plus 1, 4 plus 3, 7. So 7, all the reds here. So this forms the denominator for your precision. Okay, remember that, because the precision is nothing but true positives by total number of predictions, and recall is nothing but true positives by total number of ground truth. So now let's create that table which can help you in the precision recall curve. So what we are going to do is we are going to change because predictions are the ones which are coming one after the time, and ground truth is already known to us. So we will keep the recall as it is from the start, but precision will calculate one image at a time. So what is the first step? First step is like sort by the score, the confidence score. So this is the guy we will consider first. So 0.9 image 3. Okay, so image 3 0.9, it's a true positive. And what is the precision? So your prediction number 1, so you only have one prediction to start with. That's what I said, prediction will go one by one. The recall, the ground truths are already available to us across all the images, so we'll consider full. So 4 detections are totally there. So your recall value is true positive, which is already 1. So this is true positive actually. So 1 by 1. So true positive by total number of predictions so far, which is 1. So 1 by 1. True positive by total number of ground truth, which is 4, which is already available. So it's 1 by 4. Now again the next one is 0.8, this guy. So it's false positive. So that means you cannot add numerator here because it's not true positive. So this remains 1. But now we have 2 predictions. So 1 by 2. This will remain the same because it's false positive. Now image 1.7. So image 1, this guy, it's true positive. So that means I can add 1 to the numerator. So 1 plus 1 will become 2. You have 1, 2, 3 predictions. So 2 by 3. It's kind of cumulative. The precision is kind of cumulative. Recall, you have 2 here now because this 1, the 2, and total ground truth is 4. So 2 by 4. So this is now the values of precision and recall. Now next one. So out of this should be 0.6. So 0.6 is false positive, so you cannot add the numerator, but the prediction is increased by 1. So 2 by 4, 2 by 4. Similarly, you can go in image 2.5. This is true positive, so I can add 1 to the numerator. So 3, total number is 1, 2, 3, 4, 5 predictions. So 3 by 5. The total ground truth was 4, so 3 by 4. So I can just go on and complete this table. So if you have confusion, you just go by one by one and understand this what's happening. And now I have the precision values, I have the recall values, I can plot a curve. So you start with this recall, this value is 1, and then you have somewhere around 1 by 4 is 0.25. So they are kind of having, you see this value is remaining at 1, which is the recall space. Okay, so that's the same value you can think of. And then it drops to 0.5, which is what exactly here. So it dropped to 0.5 for the corresponding recall values. So why this is extrapolated actually, because there's nothing at 0 for us. It starts at 1 by 4, 1 by 4. So at 1 by 4, 1 by 4, which is somewhere here, 0.25. It has both 1 and 0.5, right? The precision has both 1 and 0.5. So that's marked here. And similarly others you kind of plotted. And this blue shaded region is the area under the curve. So area will be coming to around 0.53. So that's the average precision. So remember that average precision for the class dog. Now you need to repeat this for another class. Maybe if it's a cat, you need to repeat this exercise for that class. So you'll get the average precision for cat. Similarly, there may be a horse in the data set. So you'll calculate the average precision for horse. Now you need to have mean average precision, which means you average across all these average precisions. So average precision of cat plus average precision of dog plus average precision of horse divided by 3. So that's what the mean average precision means. So this is the formula for that. So average precision for each class you find, then you average across or mean across all the average precisions. So I hope now it makes a bit of sense. I have 2 more examples, so you'll get much better understanding. Of course, I'm not going to do mean average precision, but average precision only. But let's consider this. So this is again a very good website. They'll give a code for object detection metrics as a library. So you can literally use it for many purposes. But let's quickly go through this. So there are many predictions here. The explanation is here. So the class is cat. So we only consider average precision here for the class cat. And about so many images shown here. And there is a total of 12 target objects limited by the green boxes. So green is your ground truth. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 green boxes. Those are your ground truth. So total number of ground truth is 12. And then you have so many predictions. So let's now calculate the average precision step by step. So total ground truth is 12 in this case, and you can consider the total predictions also. This is 12. So the denominators are fixed. So again, we will consider the ground truth prior available. So the recall calculations will always choose the numerator as 12. The precision calculation will go step by step. So let's put it into a table. So here key factor. So earlier in the previous case, I just manually or as a human, I put it into false positive and true positive. But the actual way of doing is you calculate the IOU and then put a threshold, and based on that threshold, you say it's true positive or not. This IOU is with respect to the ground truth. Okay. So the percentages you see over here are the classifier score. So you sort that by the class. So you consider all the bounding box predictions. You sort them by the classifier score. That's this row. You sorted it already, right? D, which is here, is 99%. That is a top. Now you find the IOU score between this the green and the red boxes. The red is the prediction and the green is your ground truth, and that comes to be 0.91, which makes sense. They are very close. And this is now considered with the threshold. You choose the threshold. This 0.5 has a meaning, so remember that. Okay, so it's above 0.5, so this is true positive. Similarly, you consider K. So where is K? K is here. So there is this IOU. There is definitely, it's not as good as 0.91, so it's 0.7 and it's above 0.5. So I consider this as yes. So similarly, you consider the IOU scores for all of them, and then if it's above 0.5, you put yes, it's true positive, and if not, it's no, it's false positive. Okay, so that's the idea. Now let's fill this table. Okay, so cumulative as we discussed, and precision and recall. So let's say the first one, this is true positive because it's yes. Okay, so true positive, so that means precision will be 1. And how many detect predictions now? It's only 1. So 1 by 1, this is 1. What about recall? It should be 1 divided by the total ground truth, which is 12. So 1 by 12 is approximately 0.0833. You can do the calculation. Now let's consider this. This is again true positive. So two true positives out of 2 detections. So precision is not changing. This will change because 2 by 12 will become like 2 times of this, right? So 0.1667. This is again true positive. So this will not change. This will change because true positive, the numerator is changing. Denominator remains 12 all the time. This is also yes. This is also yes. I'll just keep on going till the no. So till here, 8 true positives out of 8 detections. So precision is 100%. And this is like 8 by 12, which is somewhere around 0.6667. Okay, so that's the idea. Now there is first false positive here. You see J is this guy. So this is actually false negative if you want to think that way. But as I said, sometimes we treat it as false positive, and most of the time for MAP calculation, because it's just a false detection. So false positive here, and there is no IOU, so there's no possibility of IOU, so this is false positive. And then this will become our first, so this will not change. 8 true positives out of 9, right? So 8 by 9 is 0.8889, and this will not change because the true positive remains same and the ground truth is same. So 8 by 12 is still 0.667, and you keep on doing for the others and not. And then you plot this against this, the precision against recall, you get something like this. And you calculate the area under the curve, which will be these shaded regions. I can just show it for you. So this entire region, so this is area plus this, right? So this plus this will be your area, and that's pretty high, right? So the average precision is pretty high here, so that means model is performing decent, which you can see from the result. If you assume your IOU score is above 0.85. sorry 0.5. So this is average precision with respect to IOU of 0.5. And if you do this for other classes, let's say the boy or the person or the horse, and then find out the average precisions for each of them and mean across it, this is called mean average precision with IOU equal to or greater than equal to 0.5. So this is what popularly known as mAP at IOU equal to 0.05. If you go to YOLO results and all, some of you already done or used your YOLO for many purpose. So this is the meaning of it. Okay, I hope it's clear. Okay, so that's it. So the area is decent. So that means mAP or IP at 0.5 IOU is fine. It's good. Now let's redo this exercise for a slightly higher IOU threshold, which is 0.75. So then this is yes, this is true positive, but this guy becomes no now because it's 0.7, which is lower than 0.75. So this is a false positive now. Similarly, this becomes yes. So you see this table, and now you go back here. This is true positive, so 1 out of 1. This is fine, but here this is no more a true positive. So that means 1 out of 2 detections. So 0.5. This will not change. So you can calculate. You just do yourself. Don't skip this. You please take your time. Fill this table. So you hide these two. You fill this one by one, and you understand this, and then you plot the curve. And now you can see this is not good as the previous. So I increase the threshold to 0.75. Your model performance has come down. So you now have the area. So this region plus, so this region, right? So this region plus this region is much lower than the previous case. So the performance of this model, and you can call it as AP at IOU greater than 0.75, is much lower. And if we had done this exercise over other classes, you can call this as MOU at 0.75. So most of the modern day object detection, they do MAPs at 0.05, 0.75, and then average that also to kind of have a holistic measure. So I hope it's clear. So let me reiterate this entire idea once more. It's a slightly long session, but I hope you can make sense of out of it now. So we started the story from IOU. Then we used it for suppressing the redundant bounding boxes created by region proposal, which we call as non-maxima suppression. That was done. And then use the IOU for finding the goodness of your prediction with respect to your ground truth. So IOU is high means it's true positive. IOU is very low means it's false positive. So that's the way we generally use it. And then based on IOU, I can create the precisions and the recalls, and I can form the precision recall curve, and then I can measure the area which forms the average precision. I can repeat it for different classes and take the mean of all the average precisions for each of the classes. It becomes mean average precision. And don't forget, precision is how good is your model in the prediction. True positives divided by total predictions. That's precision. Uh, Recall means true positives divided by total detections. Out of all the ground truths, how good is the prediction? How good is your model? Right? So it makes sense in that scenario. So that's what we discussed in this slightly long session.